Okay, so at the end of the last lecture, we were talking about stacks, right? So just to quickly remind you, these are examples of physical stacks, right? So stack of files, stack of books, stack of pancakes, right? There's the notion of the top of the stack. Everything in the data structure called the stack happens at the top of the stack, right? So I can add elements to the top of the stack. I can remove elements from the top of the stack, but I'm not supposed to be able to remove elements from the middle of the stack. Right, so classically, there's two operations, push and pop. Right? When you push an element onto the stack, that means you're adding an element to the top of the stack. So if I push a string A onto the top of the stack, you get a stack of size 1, size 2, size 3, and so on. Right? Popping an element from a stack removes the element at the top of the stack, returns the element back to the caller. Right? So if I pop the element, the caller gets back the E, and then the element is removed from the top of the stack. Right? Pop it again, they get back the D, right, and the C, and then the B, and the A. Now notice that the order of which things happen. Right? So when you add elements to the stack, right, the stack grows up, right, and you get you have the sequence A, B, C, D, E. But when you remove the elements, they come out in reverse order, right? So when you remove the elements, they come out E, D, C, B, then A. Right? So a stack's called a LIFO, so last in, first out data structure. And then we looked at an implementation of a stack using an array list. So I'm not going to go over that right now. Instead, I'm going to talk about one use of a stack. Right? So one possible use of a stack is when you have a recursive method and you want to turn that recursive method into an iterative version of a method. Right? The problem with recursion is that often there's a limit to the size of the problem that you can solve. And you'll see why that's the case shortly, right? And whereas the size of the corresponding iterative solution is usually much larger, right? The size of the problem that you can solve is usually much larger. So the key to understand how you might use a stack to convert a recursive method into a non-recursive one is to draw a picture of what's happening. And this should also explain to you what happens when a method is called in Java or a language like C. Python similar too. So here's a method that you should never really write in practice unless you're taking an introductory computing science course. Right? So when you're learning recursion for the first time, it's very common to give you small problems that are easy to understand, but that you would actually never implement recursively. So here's a method called power of 10. It simply computes 10 to the power n. Right, where n is a value greater than or equal to 0. Right, so it's a recursive method, so I have a base case up here. Right, so if n is 0, I know the answer is 1. Right, 10 to the 0 is 1. Right, if n is not 0, then I'm going to recursively compute 10 to the power of n minus 1. Right, and then I'm going to get that answer, and I'm going to multiply it by 10. Right, so 10 times 10 to the n minus 1 is equal to 10. 10 to the n. Right? And then when you're done, you just return the result. Right? So there's a simple little recursive method. Again, you would never write it this way. Right? But this is what happens when you call that recursive method with the power, or with the value of n equals 3. Okay? So when you call a method in Java, or C, or Python, what happens is that some memory gets allocated for the method to run in. Right? So when I call power of 10.3, right, the method starts running somewhere in memory. Right? And the space that's allocated for that method includes the memory needed for all of the local variables or parameters of the method. Right? So power of 10 has a parameter n. Right? So space is allocated for n. Right? When you call it with power of 10.3, the 3 gets copied in as the value n. Right? We have a variable called result, right? A local variable called result. Right? So space is allocated for that variable as well. Right? And then there's a bunch of other stuff that's allocated that we don't need to worry about for now. Right? If you ever take a compiler's course, they'll tell you exactly what else is sitting in this, what's called a stack frame. Right? But for our purposes, we don't care about the other stuff. Okay? Okay, so what happens when you call power of 10.3? Right? Well, it's recursive, so it calls itself. right? It computes 10 times power of 10 2, right? Now what you need to remember in a recursive method is that the method, whenever you run a method, a new chunk of memory gets carved out for that method. So in other words, power of 10 does not run in this chunk of memory. It runs in a new chunk of memory. Right? So you get a new block of memory who has storage for n result. Right? Now n is 2. Right? The result is now 10 times the power of 10 1. Right? So that's another method call. So more memory gets carved out. Right? The value of n is 1. Right? The result is 10 times power of 10 to the 0. So power of 10 runs again. Right? This time n is 0, which is a base case. Right? So now we know what the answer is. Right? So we reach the base case. I know that the result is 1. Right? And then the method finishes running. Right? So when a method finishes running, it returns its result back to the caller. Right? So that 1 is going to come back up and replace power of 10 0 here. Right? So I'm going to replace that with 1. Right? And now this method is complete. Right? It's returned its value. Away it goes. So it disappears from memory. Right? And now this version of power of 10 can compute its final result, which is 10. So that 10 gets passed back up to the previous version of power of 10. Right? And then this can go away. Right? And we can calculate 100 here, like that. Right? This can get passed up. Right? That can this can go away, and that value becomes 1,000. Right? And that 1,000 now gets returned back to the main method. Right? And then finally, this can go away. Right? All right. So if we reverse that process, right, to see what happens again, right? We call the method. So there it is. It calls itself. Right? It calls itself. It calls itself. Right? So if you just flip that picture upside down, that's a stack. Right? That's the top of the stack. Right? When that finishes running, that disappears. Right? So in other words, we pop the stack. Right? That's now the top of the stack. When it finishes running, we pop the stack. Right? That's the top of the stack. When it's done running, we pop. Right? That's the top of the stack. When it's done running, we pop it from the stack. Right? So those methods, right? Those methods that look like they're on a stack, that's actually called the call stack. Right? So it's a stack of method calls. Right? And so that's what happens when you call the recursive method, right? Or any method. Right? Whenever you call a method, it calls some other method. They all just get pushed onto a stack. Right? So if you have a recursive method, you can convert that to its iterative form by using a stack, right? And you simulate everything that Java is doing for you. Right? So in other words, I'm going to manually simulate the call stack process. Right? And the basic idea is you push some information onto some kind of stack to remember what needs to be done when the recursive call returns. Right? So in other words, if we go back and look at our recursive method, right, I need to remember what do I need to do with this return value, right, every time that the method returns. So let's take a look at how that works. Okay, so in power of 10, what needs to be done when every recursive method call returns? Right, so when a method call returns, it returns back some value, and then you multiply the return value by 10. Right? So that's what the recursive statement says. It says it's 10 times power of 10 n minus 1. Right? So we multiply the return value by 10. Right? So keep that in mind. So how are we going to simulate that using a stack? Right? So I'm going to use a stack of integer values, right? And I'm going to push a 10 onto the stack of integer values. Right? So each recursive call that's not a base case pushes a 10 onto the stack. That's how the power of 10 method actually works. Right? It just pushes 10s onto the stack. During each recursive call, what happens to the value of n? Right? Well, it's a recursive method. Right? The base case is that n equals 0. In the recursive case, n is greater than 0. So every time you make a recursive call, n has to get smaller. Right? Only one of these has n decreasing. Right? So that's n decreases by 1 each time. Right? Every time you call power of 10, you decrease the value of n by 1. Right? That's why it says power of 10, n minus 1. Right? So what's our iterative version of the method going to look like? Right? We're going to start out with an empty stack. right? So that represents the call stack where we haven't called power of 10 yet. Right? It's a stack of integer because all I need to remember is the return value. In this case, all I need to remember is the return value. Right? So while n is greater than 0, right? So this is going to be my iterative simulation of calling each version of power of 10. Right? So while n is greater than 0, I'm just going to push a 10 onto the stack every time. Right? And then I'm going to decrease the value of n by 1. Right? So that simulates the return value. Right? That simulates calling, this simulates what you have to do with the return value. Right? So I need to return the return value by 10. I need to multiply the return value by 10. Right? The n minus minus simulates calling the recursive method, right, with a new value of n, right, with a smaller value of n. Okay, so once you've done that, you've got n 10s sitting on the stack. Right? Okay, so now I want to simulate, all right, now I need to simulate the base case. Right? So a recursive call that reaches the base case returns a value of 1. Right? So here's my base case. Right? The result is 1. Right? And now I'm going to unwind the call stack. Right? So right now I've simulated the n calls to power of 10. Right? This bottom one has returned 1. Right? And now I'm going to unwind the call stack. Right? So each time the top element of the stack is done, right, we pop it from the stack and multiply it by whatever's sitting on the other stack, on this stack here, on T. Right? So I'm going to pop the stack until it's empty, multiplying the values as we go. Right? So I'm going to take result, right, and I'm going to multiply result by whatever's sitting on top of this stack T. Right? And so that simulates the 10 times whatever the result is, part of the recursive method. Right? And you just do that until the stack is empty. Right? And that produces the final result. Right? So there's an example of simulating a recursive method using a stack on your own. Right? Now this is not, in this example, this is way too complicated. Right? You would never write power of 10 this way on your own. Right? If you had to implement power of 10 on your own, you'd just use a loop, right, and multiply 10 n times. Right? But that's actually simulating what happens in the recursive method. And it turns out you can do this for any recursive method. Right? What you end up storing on the stack becomes a lot more complicated. Right? So as soon as you try to solve some non-trivial as soon as you try to convert some non-trivial recursive method, right, you end up not using a stack of integer, but a stack of something else. Right? Where the something else depends on the problem that you're trying to solve. But this illustrates the process of what's happening. Right? So you can take any recursive method, convert it into a non-recursive method using a stack. Right? Okay, so there's a little detour on recursion and how to use a stack to simulate a recursive method. We now want to go back to actually implementing a stack. Okay, so our array list version of the stack actually tells you how you should implement a stack if you want to use something else, right? So if I want to use an array, right, then I can implement a stack using an array by simulating what the array list is doing. Right? So remember, in the array list version of a stack, when you push an element onto the stack, you add an element to the end of the list. Right? When you pop an element from the stack, you remove it from the end of the list. Right. If I want to use a plain old array, I have a problem when I push elements onto the stack, right? Because eventually you'll run out of space in the array. Right? In an array list, it doesn't matter, right? You never conceptually run out of space, right? You just keep on pushing stuff. You just keep on adding stuff to the end of the list, and the list takes care of allocating memory for you. If you're going to use a plain array, that's not the case. Right? So eventually your array runs out of space, and then you can't add anything to the array. Right? So the solution in this case is that you make a new array. Right? And so you make a new, larger array, copy the elements from the old array into the new array, and then continue. Right? Now the other thing with the list is that the list knows its size. Right? It knows the number of elements in the list. Right? So that lets me remove the last element of the list very easily. right? I just ask for the list size and subtract 1, and that's the index of the last element. An array doesn't remember how many elements are in the list, right? It knows how big the array is, so it knows its capacity, right? But it doesn't know how many elements you've actually inserted into the array, right? So now we have to keep track of that as well, right? So we need a field to store the index of the top element, right? So remember, in the array-based list, the index of the top element is just the size minus 1, right? I don't have the size of the array, right? I don't have the number of elements in the array, sorry, so I have to keep track of that myself. So we're going to use an index, right, that points to, or that indicates the element in the array that's the current top of the stack. Right? So our stack is going to be a stack of integer values, so it's called an int stack. Right? Internally, I'm going to use an array of int to hold the elements. Right? I'm going to have a field called top index that's equal to the index of the top of the stack. Right? So if the stack is empty, that index is going to be minus 1. Right? So if your index is invalid, then you know that the stack is empty. Right? If the index is negative, you know that the stack is empty. Right? What does the constructor do? So the no argument constructor makes an empty stack. Right? What does every constructor do? It initializes the fields. So I have to make a new array, and I have to set top index. Right? So I make the array, new int, some size. Here I'm using a private final field called the default capacity. Right? Its number is just 16. You can use any non-zero value here, it's fine. Right? And then I'm going to set the top index to minus 1 to indicate that the stack is empty. So that's the picture of your stack. That's the picture of the memory of your stack when you make an empty stack. Right? So top index is minus 1. Right? I've got an array of size 16. Right? All the values are 0 because that's what Java does when you make a new int array. Right? It sets everything to 0 for you. The numbers in the boxes are not important for our purposes. Right? So the fact that these are all zeros, it doesn't matter. Right? Because when I put something into the array, I'm just going to overwrite that value anyway. Okay? So pushing a value onto the stack. Right? So if I'm going to push a value onto the stack and I have room in the array, right, then all you do is you add 1 to top index, right, and then set the element in the array at that index. Right? So if I push a 7 onto the stack, right, I add 1 to top index to get 0, right, and then I set the array at index 0 to the value that was pushed. Right, so I set it to 7. Right, so I just overwrite the 0 and set that to 7. And so there's a picture of your stack now. Right, if I push a minus 5, right, add 1 to top index to get 1, right, then set the element at index 1 to minus 5. Right, and so on and so on. Right? So if you keep on pushing elements, you just keep on overwriting these zeros, right, adding 1 to the top index every time. Okay, so if you pop a value from a non-empty stack, what do? Right, so when you pop a value, you have to return that value back to the caller. Right, so if I'm going to pop that minus 5, I have to remember what the minus 5 is, so I give it back to the caller. And then obviously I'm going to decrease the top index by 1. Right? So I'm going to get the value at the current top index of the array. Right? Then you decrement top index by 1. Right? And then you return the value. Right? You don't have to overwrite what's sitting in the array. Right? So in other words, right, when I pop the minus 5, right, I'm going to get the value of the minus 5 first. Right? So that's value equals minus 5. Right? I'm going to get that value. I'm going to decrease the top index by 1. And then I'm going to return that minus 5 back to the caller. I don't have to overwrite that minus 5. Right? There's no reason for me to overwrite the minus 5 in this case. Right? Because when you push something onto the stack, you're just going to overwrite that value anyway. Okay, so what does pop look like? Well, first of all, I have to make sure that the stack is not empty. Right? But if the stack is empty, right, so if top index is minus 1, right, there's nothing on the stack to pop, so I'm going to throw an exception. Right? In this case, it throws the empty stack exception. Right? If you get past the validation, right, then you just do the 3 steps that I told you, right? You remember what's the current what's the current value at the top of the stack, right? Decrease the top of the stack by 1, and then return the element. Right, so pop's easy. Okay, so what about push? We have to come back and finish push, right? Because eventually, if you push a bunch of elements onto the stack, you're going to run out of space, right? So if there's something sitting here and I try to push another element on it, there's no space in the array, right? So this is the state of the stack when you can safely do one more push, right? So if I have one more spot left in the array, I can go ahead and push an element onto that stack, right? So what's the condition where you can safely push? Well, if the top index is less than the size of the array minus 1, right, the length of the array minus 1, right, then I can safely push onto the stack, right? So if the top index is less than the length of the array minus 1, right, go ahead and push the element onto the stack, right? Increment the top index by 1, set the value, and you're done. Right? Now, what happens if this condition is not true? Right? So if there isn't more capacity in the array, right, I have to do the following. You have to make a new array with greater capacity. Right? So in other words, I have to replace my existing array with a new array, and it has to be bigger than the current array. Right? Now, if I replace that array, I have to copy all the elements from the old array back into the new array. Right? Otherwise, I lose all the elements on the stack, which I don't want to do. Right? Now, I have a new array, so I have to point my field, this ARR, so that it equals the new array. Right? So it points to the new array. Right? And then I now have space in the array, so I can just push the element onto the stack now. Right? So make a bigger array, copy the old array into the new array, adjust this ARR to refer to the new array, right, and then push the element onto the stack. Okay, when I make that bigger array, I have to decide how much bigger should that array be. Right? So should I make it 1 bigger? Right? Should I make it 2 bigger? Should I make it 10 bigger? Or should I do something else? So it turns out the answer is you should do something else. All right, so when I make my new array, right, so here's my new array, it's called new array. Right, I'm going to make a new array of int, and I'm going to double the current capacity. Right, so I'm going to take the current capacity, multiply it by 2 in this case. Right? Now it turns out if you increase the size of the array by some positive factor of the current capacity, right, then you can mathematically prove that the complexity of adding, of pushing an element onto the stack is on average big O of 1. Right? So on average, it's big O of 1. Right? Every once in a while, right? So whenever I have to make a new array, right, I have to copy all the elements into the new array. Right? That copying process is big O of n, right? Because you have to copy the n elements on the stack. Right? So every once in a while, whenever you have to increase the capacity of the stack, the cost of push is big O of n, right? So the worst case complexity for push is big O of n when you use an array, right? That's also true when you use an array list, right? It's also big O of n. That's the worst case complexity. But on average, as long as you increase the capacity of the array by some constant factor, right, it's big O of 1. So that doesn't have to be 2. It could be, for example, 1.5 or something like that, right? And I believe it's 1.5 that's used in the standard implementation of array list. Right? So an array list is just a list that has an array to store the elements, and it does exactly this when you add something to the list. Right? It checks is there space in the array. If not, it expands the size of the array. Right? So I'm going to multiply it by 2 instead of 1.5. You can choose any positive factor here. Right? You don't want to choose a value that's too big because that ends up wasting a lot of room. Right? You don't want to choose a value that's too small because that increases the number of times you have to reallocate the array. Right? If you, instead of increasing it by a constant factor, so if I add, say, one element if I add 1 unit of capacity every time, that turns out to be very bad, right? So if I increase the size of the array by 1 every time, right, that lets me push a new element onto the stack, right? It costs me O(n) time because I have to copy the n elements, right? If I then push another element onto the stack, I have to reallocate the array again, right? So now it becomes O(n), right? So again, I have to allocate space for one more element, right? Copy the existing array into the new array, right? That's big O of n, and then push the element onto the stack, right? So if you increase by a constant value every time, right, instead of a constant factor of the current capacity, right? So if you increase by some constant number, 1, 10, 100, it doesn't matter, right? Then the worst case complexity becomes big O of n all the time, right? So that's why you have to increase by a constant factor. You have to increase the capacity by a constant factor, right? We want to try to get big O of 1 on average for push. Once you've made the new array, copy all the elements from the old array into the new array, right? Just use a loop. Set this ARR to equal new ARR, right? So in other words, make the field point to the new array, and then go ahead and push the element onto the stack, right? Notice that our implementation of push is now recursive, right? Because it's going to call itself. But when it calls itself, it falls immediately into the base case, right? And pushes the element onto the stack. If you wanted to, you could just copy these 2 lines of code and stick them here instead, right? All right. Any questions about that? Okay, so when you're working with arrays, it turns out it's very common that you have to do this. You have to do this reallocation and then copying of the old elements into the new array, especially if you want to implement something where you don't know the number of elements that have to go into the array ahead of time, right? So if I want to use an array and I want the array to be able to grow in capacity, this is exactly what you have to do, right? Now, because it's common, the designers of the language added a method that does this for you, right? So arrays.copyOf will create a new array for you of any capacity that you ask for, and then copy the elements of an existing array into that new array for you, right? So instead of writing this, you can just write that, right? So instead of allocating the array yourself using new, right, call copyOf, pass in the array that you want to copy, right, pass in the capacity of your new array, right, and it does all the work for you, right? Then all you have to do is set this ARR to point to your new array, and then push the element onto the array, onto the stack. Right? Okay, so that's how you implement an array-based stack, right, instead of using an array list-based stack. Right? It's a little harder to do because you now have to keep track, because now you have to manage your array yourself, right? Whereas when you use an array list, you just ignore all of this memory management and copying and so on and so forth, right? You let the list take care of all of that for you. Right? Now, if you take CISC124 next year, I guess, or in the summer, you end up programming in a language called C, right? So in C, or C's standard library, there are no lists. Right? There's actually no data structures whatsoever. So all you get are arrays, right? So in C, you end up doing all of this stuff all of the time. You end up doing stuff like this all of the time on your own. Okay, so let's look at a different implementation of the stack. Stack 2, where's stack 2? It's dot here. All right, so, oops, sorry, hang on. All right, bear with me while I grab the lecture file. Just a second here while I check what's going on here. Okay. All right, so we now have 2 implementations of a stack, right? We've got an array list-based stack. We have an array-based stack. Later today, I guess, we're going to start to implement a stack in a completely different way. We'd like all these stacks to be interchangeable. Right? So in other words, I'd like someone, it'd be nice if someone could use our array list-based stack, right? Or if they wanted to, they could use our array-based stack, right? And the two stacks would be completely interchangeable, right? So in other words, I can write a method that takes in either an array-based stack or an array list-based stack, right? And the method works exactly the same way, right? In other words, you don't have to change the method based on the implementation of the stack. Right? Now, one way to do that in Java is to create an interface for all stacks, right? And then have our classes implement the stack interface. Right? So this works especially well for stacks, because stacks, they only have a few methods, right? They have size, you can ask it if it's empty, you can push an element onto a stack, you can pop an element from a stack. Right? So all of our stacks, they have common methods. So this is a perfect example of creating an interface for our different implementations. Right? So remember what an interface is? It's just a list of methods, right, that every class that implements the interface has to provide. Right? So we have our interface called stack, right? So you use the keyword interface instead of class to indicate that the stack is an interface. Right? We have a method called size, right? It returns an int, right? And that returns the number of elements in the stack. Right? I'm going to skip over is empty for now. We'll come back to that in a second. Right? All of our stacks have a push method, right? And all of our stacks have a pop method. So notice that this interface is a stack of strings, right? It's not a stack of ints anymore. It's a stack of strings. We'll come to that issue. We'll address that issue shortly. Right? And so that's your interface. You've got 4 methods in your interface, right? There's no fields, right? Notice there's no fields. So this interface does not say anything about how the stacks are implemented, right? It doesn't say that a stack has an array list. It doesn't say that a stack has an array. It doesn't say a stack has something else, right? All it says is that a stack has these 4 methods. Right? Now there's this method here that says default in front of it. Right? So we have what's called a default method, and it has a method body. Right? So in other words, it has an implementation. Right? So a default method in an interface is a method that provides an implementation of the method. Every class that implements the stack interface gets the default implementation. Right? If you include a default method in an interface, right, then the implementation of the method, right, you have to do it in terms of the methods of the interface. Right? So is empty I can implement, right? Because right, I don't know what the stack is made of, right? I don't know that there's an array list here. I don't know that there's an array here, right? But I do know that there's a size method, right? Because that's what the interface says, right? Furthermore, I know if the size is 0, the stack is empty, right? So I can simply return this size equals 0, right? So this is legal to write in Java, right? So if you can implement a method in terms of its, if you can implement a method in an interface in terms of the other methods of the interface, then you can provide an implementation of the method, right? Okay, so so interfaces are allowed to have these things called default methods. Classes cannot have default methods, right? Classes just have methods. Right? A default method is a method in an interface that has an implementation, right? The implementation can only use methods from the interface itself, right? So that's fine. It is allowed to use methods from java.lang.object. Right? So you can use toString equals hash code if you want to for some reason. Right? So you're allowed to use those methods. Why? Because some class has to implement this interface. Right? Every class gets the methods from object. So you're allowed to use those methods. Right? The third one, you're allowed to use any methods from the super interface of the interface. Now, that probably doesn't make any sense to you right now. We'll come back to this later. Right? An example, though, is that if you had a default method in list, right, then that method could be implemented in terms of the collection interface. Right? So if you remember back, I think 2 or 3 weeks now, that the list interface, right, is actually a sub-interface of the collection interface. Right? Or the collection interface is actually what's called a super interface of list. Right? List has every method that's in collection. Right? So you can use the methods from collection to implement a list default method. Right? This will make more sense to you in a week or so. Right? For now, it's these two that are of interest to us. Right? So default methods are new-ish. Right? So new-ish. They were added in Java 8 of the language to address a specific problem. Right? So the problem with interfaces is as follows. Right? Suppose you make an interface. Right? It turns out lots of people want to use your interface because you implemented some interface that's really useful to have. Right? So for the Java standard library people, they've got all sorts of interfaces, right? List, set, map, right? Lots of people are using the interfaces. The problem with interfaces is once people start to use the interface, you can't change the interface anymore. Right? If you add a new method to the interface, right, everybody who used your interface has to recompile their code. Right? Because not just has to recompile the code, they have to change their code to implement the newly added method. Right? And that's wildly impractical in software engineering. Right? If you remove a method from an interface, now everybody's code that uses your interface breaks because they're probably using the method that you removed, and that method no longer exists in the interface. Right? So once you have a widely used interface, it's impossible to change the interface. Right? Well, impractical, not impossible. Right? It's very impractical. Okay, so what happened in Java 8? So Java 8 came along and said, well, we're going to add these features called Lambda Expressions, right? Which we don't cover in this course. If you take the Programming Paradigms course, you're going to see something called functional programming. And so that's what Lambda Expressions try to simulate in Java. Right? But anyway, Java added a very significant update to the language. And the problem is that update affected almost every existing interface. Right? And so now you have a problem. Right? I want to add a new feature to the language. I have to change the interfaces, but I can't because it's going to break everybody's code. Right? And so what they did is they added these default methods. Right? So by adding the default methods, you provide an implementation of the method. Right? And that means anybody who's using your interface and implemented a class that implements your interface, right, that class gets, their implementation gets the default method for free. Right? They have to recompile their code, but they don't have to change their code to add the new method. Right? And so the designers of the Java language decided that this was preferable. Right? So adding default methods was preferable to breaking everybody's existing code, right? Which was probably a good decision. Right? And so that's how they added this new feature to the language. Right? They were forced to also add default interface methods. All right, so I've now got an interface for stacks. I have two implementations of a stack. I should change those implementations so that they implement the stack interface. Right? I can't actually do that, though, for our array-based stack. Right? Our array-based stack is a stack of int. Right? It's not a stack of strings, right? Which is a bit of a problem. But we're going to fix this in about a week. OK, so here's our list stack. Right? That's our array list stack. Right? I'm going to change its name to list stack to indicate that it's actually using a list to implement the stack. Right? And then I'm going to say that it implements our stack interface. Right? And that's it. That's the only change I have to make. Right? Because the methods in this class are size, push, and pop. Right? I get the isEmpty method for free. Right? So all I have to do is change the name from stack to list stack and say that it implements the stack interface. So that was straightforward. I'm not going to do the array-based stack yet because that forces me to change the array-based stack, the int array-based stack to a string array-based stack. So instead, I'm going to talk about implementing a stack in the third way. Okay? And so the third way that I'm going to implement the stack is to use what's called nodes. Right? All right, so why do I want to do this? It's because if you use an array-based stack or an array list-based stack, right, push has worst-case complexity big O of n. Right? Whenever you have to resize that internal array, that's big O of n. Right? Which means your push operation can become relatively expensive every once in a while. Right? If for some reason you need to guarantee that push has big O1, right? So in other words, if you are implementing a stack and you need it to have guaranteed high performance, right? In other words, you can't afford to pay the price, or you're not willing to pay the price of occasionally having it be a little slow, right? Then you have to change your implementation, right? And so I can guarantee big O1 if we change the way that we store the elements. Okay, so many data structures represent a collection of elements using nodes. Right? So you're going to see a linked list later in the course. Right? If you take CISC124, the data structures course, you will probably see trees. Right? You might see graphs. You'll definitely see graphs in CISC365, the algorithms course. If you take Math 401, that's a graph theory course. You'll probably see nodes as well. But these node-based implementations are extremely common, especially when you use a language like C. Right? So what's a node? Right? So now I need to tell you what a node is. So a node stores an element. Right? So it's going to store, we're actually going to store our elements of the stack in a node. Right? Sorry, we're going to store each element of the stack in one node. Right? And then the node stores a reference to 0 or more nodes. Right? And so these references are often called links. Right? So what does that look like? So I'll show you a picture of that in a second. Right? So our node stores one element, stores a link to one or more other nodes. 0 or more other nodes, sorry. All right, so that's in general what a node looks like. So for a stack, right, a stack is a linear collection of elements. Right? There's one element followed by another element, followed by one more element, followed by another element. Right? So it's, if you draw a picture of it, it looks like a line. Right? The elements are arranged in a sequence, right? Starting from the top element of the stack, going down to the bottom element of the stack. Right? I'm going to connect each element. Each element is connected to the next element that's deeper in the stack. Right? So the top element is connected to the second. Right? The second from the top element is connected to the third, and so on all the way down to the bottom. Right? But the top element is not directly connected to the bottom element. Right? Okay, so a node in a stack then is going to store an element, and it's going to store a reference to the next node deeper in the stack. Right? So I'm going to draw a picture that looks like this. Right? So that thing there, that's my node. Right? So I have the element in the node, and I've got this arrow that points to the next node in the stack. Right? Now, if that's the top element in the stack, there is no next element. Right? So it points to null. Right? Remember, null means no object in Java. Right? So that's one node. Right? There's my element. That red arrow and the value that it points to, that's my link. Right? So when I push an element onto the stack, right, if I'm going to use this representation, what do I have to do? Right? Well, I need a new node to hold the new element. So there's my new node. Right? I need to connect that node to the existing node that's on the stack. Right? So set the link of the new node to point to the current top node. Right? So in other words, I need to do that. Right? So I need to link the B so that it points to the A. Right? Now that's the new top of the stack. So I have to move top so that it points to B. Right? And so that's not what your stack looks like now. Right? And then finally, I have to add 1 to the size of the stack. Right? So step 4 is needed because all I have are nodes in the stack. Right? If I want to know the size of the stack, I have to keep track of that myself. Right? That's not precisely true, but conceptually that's what I need to do. Right? So I want to know now that there's 2 elements in this stack, right? Which means I'm going to need a field to represent the size. Right? If I push another element onto the stack, right, you make a new node, right? Make its link point to the current, to the old top of the stack, and then adjust the top of the stack. All right, now what happens when you pop an element off the stack? Right, so I want to pop this C off the stack. Right, so I obtain a reference to the element currently in the top node. Well, that's easy. I already have this pointer top. Right, so I have this thing top. It points to that node, so I can get the C. No problems. Right, so I now have my reference to C. I'm now going to move top. Right, so I'm going to set top to refer to the next node deeper in the stack. Right, now how do I get to the next node that's deeper in the stack? Right, I follow that link. Right, so if I follow the link belonging to this node, that gets me the next node in the stack. Right, so I can adjust top to point to that next node. Right, and then finally, I can remove that node from the top of the stack. Right, subtract 1 from the size of the stack to indicate that I've popped an element off, and away you go. Right, and then I'm going to return a reference to the element that was popped. Right, so I'm going to return the C. Right, return the reference back to the C. Okay, so what is a node? So what's our node class going to look like? Right, so a node in a stack, it stores, right, an element. So in this case, our node is going to store a string. Right, so our node has a reference to a string. Right, so you know for sure this relationship has to be association. Right, here I'm going to use use aggregation. Right, so in other words, the stack does not own its strings, right? Or a node doesn't own its strings, right? A node is just a reference to a node holds a reference to an existing string, right? And it holds a reference to one string, right? That string is going to be called elem. Right? So a node has a field called elem that refers to one string. Right? Now a node also has a reference to the next node. Right? So every node, right, has a reference to one other node, right, the next node. And so that field is going to be called next. Right? Notice that this is association. It's not aggregation. Right? So this is saying that node has a reference to the next node, but it doesn't own the next, or it doesn't, it's not made up of the next node. Right? Node aggregation string means that a node is made up of a string, right, and has a reference to the next node. Okay, so what is our, oh, hang on. Okay, so I'm going to do these next two slides and then we'll stop. So I want to make a class called linked stack. Right? It's going to implement the stack interface. Right? It's going to represent a stack of strings where the strings are held in nodes. Okay? I need to keep track of the size or the number of nodes or number of elements in the stack. Right? And then I need a reference to the top node of the stack. Right? So top is going to be a reference to a node that's currently on the top of the stack. Right? Now what about the rest of the elements in the stack? There are no fields to represent the rest of the elements in the stack. Right? Why are there no fields? So why is there no node called second or third or fourth? Or why is there not an array of nodes? Right? There's no extra fields because I can get to the next node by following that next link belonging to that node. Right? So if I write top.next, that's going to give me the second node in the list. Right? If I write top.next.next, that gives me the third. Right? Top.next.next.next gives me the fourth, and so on and so on and so on. Right? What does the node class look like? So our node class is just a class. It's an inner class. Right? So notice that it's a nested class. It's not an inner class. I get the terms mixed up all the time. Node is a nested class. It's not an inner class. Right? So remember that a nested class is a class defined inside of another class. Right? So node is defined inside of our linked stack class. So it's nested. It's marked static, which means it's not an inner class. Right? So what does that mean? It means that a node cannot access the size or top field of the stack. Right? In other words, it can only use its own fields. So that's what a static class, static nested class is. Right? What is every node made up of? Well, it's made up of a string called elem, right? And it has a reference to the next node in the sequence. Right? Our constructor simply sets the element to equal elem, and it sets the next node to equal to whatever that is there. Right? Okay, so we'll stop there, and then we'll look at the actual implementation of the linked stack class on Tuesday. Any questions about what's going on in the lecture? Yes? Why does it have to be static? Okay, so I'll talk about that in the next lecture. This explains everything. Okay, but that's a good question. Any other questions? All right, have a good weekend, everybody.